So far, the shortcuts covered cylinders and spheres, clean, well-behaved shapes, but not every surface is that friendly. Sometimes you need the full cross-product calculation from scratch. Pattern to recognize: whenever a surface doesn't match one of the memorized shortcuts, fall back to building the cross-product manually, using the same 3-row determinant grid used for curl. There's also a second type of surface integral, separate from measuring a scalar function spread across a surface, measuring how much a vector field pushes directly through the surface. This is called flux. Pattern to recognize: scalar surface integrals only need the cross product's magnitude. Flux integrals need the entire cross product vector kept intact, dotted directly against the field. The full cross-product grid, general setup, R sub u cross R sub v equals the determinant with I hat, j hat, k hat on top, x sub u, y sub u, z sub u in the middle, and x sub v, y sub v, z sub v on the bottom. The scalar surface integral uses magnitude only. Double integral of f ds equals double integral of f evaluated on the surface times the magnitude of R sub u cross R sub v du dv. The flux integral uses the full vector, dotted with f. Double integral of f dot ds equals double integral of f evaluated on the surface dot R sub u cross R sub v du dv. Pattern to recognize: there are no magnitude bars around the cross product in the flux formula. Direction matters here, unlike the scalar case. Worked example: find the flux of f equals x I hat plus y j hat plus z k hat through the surface R of u comma v equals u I hat plus v j hat plus the quantity u plus v k hat over the unit square, 0 less than or equal to u less than or equal to 1, and 0 less than or equal to v less than or equal to 1. Step 1. Find R sub u and R sub v. Differentiating with respect to u gives R sub u equals I hat plus k hat, that is, the vector 1, 0, 1. Differentiating with respect to v gives R sub v equals j hat plus k hat, that is, the vector 0, 1, 1. Step 2. Set up the cross product grid. R sub u cross R sub v equals the determinant with I hat, j hat, k hat on top, 1, 0, 1 in the middle row, and 0, 1, 1 in the bottom row. Step 3. Expand the determinant. The I hat component is 0 times 1 minus 1 times 1, which equals negative 1. The j hat component is negative, open bracket, 1 times 1 minus 1 times 0, close bracket, which equals negative 1. The k hat component is 1 times 1 minus 0 times 0, which equals 1. So R sub u cross R sub v equals negative 1, I hat minus 1, j hat plus 1, k hat, that is, the vector negative 1, 1. This has been verified using sympy. Step 4. Substitute f using the surface's components, since x equals u, y equals v, and z equals u plus v on the surface. F evaluated on the surface is u I hat plus v j hat plus the quantity u plus v k hat. Step 5. Dot this with the cross product vector. That gives u times negative 1 plus v times negative 1 plus the quantity u plus v times 1. This simplifies to negative u minus v plus u plus v, which equals exactly 0 for every single value of u and v, not just after integrating. This has been verified using sympy. Step 6. Integrate. Since the integrand is already 0 everywhere, we get integral from 0 to 1, integral from 0 to 1 of 0 du dv, which is just 0. Final answer. The flux equals 0. The field pushes just as much into the surface as it pushes back out, cancelling perfectly across this particular patch, and this result has been verified exactly using sympy.